Okay, so in the last lesson, if you remember, the title was finite limits as x approaches infinity. We're doing the opposite now. Infinite limits, meaning my function is approaching infinity, meaning the y value is approaching infinity as x approaches a number. So we're saying as x gets closer and closer to a normal finite number, my function's going off to infinity. And like I gave away yesterday, that's the basis for a vertical asymptote. Okay, so we'll get a couple examples, get some official definitions and everything here. So if the values of a function outgrow all positive bounds, that's a really, really fancy way of saying that the function goes off to infinity as x approaches a finite number. Here is what we write for that. We say that the limit of f of x as x approaches a equals infinity. Now, here is where we will get into some arguments in the math world, because some people say that infinity can't be stated as a limit because it's not a real number. That's totally, totally true. This is not saying that my function is approaching infinity, which is a real number. This is saying my function doesn't approach anything. It's saying my function keeps going and going and going in a positive direction. That's what this notation means. It does not imply that infinity is a real number that you can actually reach. Okay, so now let's go in the other direction. Large and negative, exceeding all negative bounds. We write just the opposite. We say the limit of that function as x approaches a finite value a is negative infinity. And again, that does not imply that it's a real number that you can actually reach. It implies that your values are just getting larger and larger in a negative direction. Okay, so just some notation there that you're going to be seeing. So look back at the graph of 1 over x from example 1. So I will flip so that you can see our graph looks like this. So as x approaches 0, see as you come in from the right-hand side, the closer x gets to 0, the larger my function value is going to be. As you come in from the left, the closer x gets from 0, the larger and more negative my function values are going to be. So this graph has both a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. So let's go back and write some stuff about that. So we observe that, here's what we've got. The limit of the function as x approaches infinity from the right is positive infinity. And we can also observe that the limit of the function as x approaches 0 from the left is negative infinity. So based on this, based on what happened here, the fact that we have infinite limits at a finite value of x means that we have a vertical asymptote. So like I said, that is the official calculus definition of a vertical asymptote. Okay, so let's write this down. We say the line x equals a. Remember, x equals lines are vertical lines. We say it's a vertical asymptote if either of the following is true. If the limit of a function as x approaches a from the right is either positive or negative infinity, or the limit of a function as x approaches a from the left is either positive infinity. Now, you could have one side going to positive infinity and one to negative infinity. You could have them both going to positive or both going to negative infinity. Any of those three possibilities, and you still call it a vertical asymptote. All right, so that's why we write either plus or minus infinity for both of these. So that is your calculus definition of a vertical asymptote. Let's look at an example here. Find the vertical asymptotes of this function. So what we're trying to do, basically, is figure out where you would have a vertical asymptote. Now, here's a little trick that I'm going to give you guys. Vertical asymptotes occur when this happens, when you get a number over 0. We talked a couple lessons ago about the difference between a whole and a vertical asymptote. They both come from having denominators of 0, but there's a huge difference. If you get 0 over 0, that gets you a whole. If you get a number over 0, that gets you a vertical asymptote. So this is still technically like the pre-calc way of finding vertical asymptotes. You've done that before. You've set the denominator equal to 0 to see when that's going to happen. So this happens when x equals 0. Because my denominator is x squared. X squared will only be equal to 0 when x is equal to 0. So we know that that's a vertical asymptote. So we found the first question. So this is what you look for. You look for a number over 0. Then describe the behavior to the left and right of each vertical asymptote. So we want to see what's happening to this function as x approaches 0 from the right, and we want to see what happens to this function as x approaches 0 from the left. Okay, so here's where we're going to use those tinies, those super official, very good way to describe limits. So, as x approaches 0 from the right, we've got a teeny, teeny, tiny number, but it's positive. Try to plug that into the denominator. Numerator is going to be 1, can't possibly change no matter what we plug in. If the denominator is a teeny, 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 tiny positive number, and then we square it, it's an even teenier, yet still positive, tiny number. Okay, so a positive 1 over a positive tiny number ends up being a positive, very large number. Okay, if I plug in a tiny little fraction to the denominator, dividing 1 by that tiny number gives us a large number. Now here, as I approach 0 from the left, it's a teeny tiny number, but it's negative. It would be like negative 0.0001. When I plug that in, the denominator is 1 no matter what. If I plug a teeny, teeny little negative number and square it, it comes out positive. Because even negative numbers come out positive when they get squared. So this is still a positive tiny number. So I actually also approach a positive infinity. So just so you get an idea, this piece of the graph looks very similar to the one that we just looked at a couple minutes ago, but the right-hand side actually mirrors it instead of going down in this bottom quadrant. So my graph is going to look something like that, more symmetrical than I just drew it, but forgive me. Okay, note about the difference between examples 1 and 4. So example 1 is the one we just referenced, and then example 4 is obviously this one. We can say that this limit exists. That's the difference. So we can say that the limit of 1 over x squared as x approaches 0 is infinity, because you're doing the same thing from both sides. The closer you get to 0, whether it's from the left or from the right, the larger your function gets in a positive direction. However, when we talk about example 1, which is 1 over x, it doesn't exist. And that's because as you come in from the left, your function goes to negative infinity. As you come in from the right, your function goes to positive infinity. So it's doing two different things in two different directions. And remember from a couple sets of notes ago, we learned that if the left-hand side doesn't do what the right-hand side does, if the limits don't agree, then the limit does not exist. All right, so it's a very subtle but important difference between those two. Okay, example 5, this isn't really something we need to solve, just kind of something to note. The graph of tangent has infinitely many vertical asymptotes, one at each point where cosine is 0. So let's make a little note about this. This is the same as sine over cosine. And we said that vertical asymptotes exist whenever you have a number over 0. So basically, whenever the denominator is 0, but the numerator is not 0. So tangent would have a vertical asymptote whenever cosine is equal to 0. So cosine is equal to 0. We'll see how well you guys recognize your unit circle. The first place, like in our normal round of a unit circle, happens at pi over 2. Okay, so at pi over 2, cosine is 0. And then it also happens at 3 pi over 2 in the normal unit circle. But you could keep going around and around and around and around. So it happened at like 5 pi over 2, 7 pi over 2, 9 pi over 2. You could go in the other direction, say negative pi over 2, negative 3 pi over 2. So basically, any odd multiple of pi over 2. So if you want to write it in a generic way, I don't know if you guys ever did this in pre-calc. A generic odd number looks like this, 2k plus 1. Because if you plug in different values, if you plug in 0 for k, you get 1. If you plug in 1 for k, you get 3, 5, 7, 9, etc. So that is how you write a very generic form of what we just talked about here, this pattern. Okay, so you're going to get vertical asymptotes at any of those places. Now, let me show you what happens. New graph here. Let me show you the tangent function. See, we've got an infinite number of vertical asymptotes, and at every single one of those values, So I'm going to draw on this, don't mind me. So you've got a vertical asymptote right there. That must be negative pi over 2. And then here's positive pi over 2, 3 pi over 2, 5 pi over 2. They just keep going like that. So as you approach the value from the left, your function's going up to positive infinity. Happens over and over and over again. As you approach the asymptote from the right, your function goes to negative infinity. Okay? So let's say the limit as x approaches, we'll just use a. Could be anything. Okay, so let's say let x equal a represent this thing right here. So the limit as you approach from the left, like we said, if we're coming in from the left-hand side, they go up to positive infinity. And if you come into any one of those asymptotes from the right, your graph is going to negative infinity. And because sine, cosine, and tangent are periodic functions, that pattern is going to repeat over and over and over again, an infinite number of times. Okay, so the last little topic that we're going to cover is something called end behavior models. It's relatively quick. It basically sums up what I was talking about with this example right here, when I said that this thing behaves like the absolute value of x, because in the end, with large values of x, the 1 doesn't matter. So end behavior models talk about what a function behaves like if you look at gigantic values of x, either positive or negative. Okay, so this thing right here, let's say we've got this complicated polynomial function and this much simpler polynomial function. What we want to do is show that obviously it's really different. Like if I plugged in 1, if I plugged in 2, these values are going to be super, super different. But the bigger of a value that I plug in for x, the less this 6 is going to matter, the less this negative 5x is going to matter, the more this polynomial is going to behave pretty much only like its leading term, which is all you have over here. Okay, so here is what we are going to do in order to show that they basically just end up identical for really, really, really big values of x. Okay, so we are going to call G an end behavior model. Okay, so here's how we are going to do that. We are going to take the limit as x approaches positive or negative infinity of f over g. Okay, I'm just going to plug it into my calculator and show you what it looks like. Okay, so 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6, and then in the denominator, just the 3x to the 4th. Okay, so in the middle here, the reason we've got this crazy function going on is because obviously if all I do is plug in 1, the numerator and denominator are going to be very, very different. But what happens, I'll zoom out here, what happens is I zoom out, I'll do it a couple times. See how my function just approaches 1. And what that means is that the numerator and denominator are so very similar that the ratio ends up being 1. And that's, I mean, if I had 4 over 4, you'd get 1 because the numerator and denominator are the same. So my numerator and denominator are so similar that my function just ends up looking like the horizontal line 1 as I go out. Okay, so either to positive or negative infinity, I end up just getting 1. Okay, so kind of just based on the graph there. So like I said, we call G an end behavior model for f because as I go out to the ends of this function, positive and negative infinity, this function looks just like this function. Okay, so I'm going to show you how to get end behavior models. For this function, if I wanted to know what this function is going to behave like, all I do is I look at the largest power. So in the numerator, this is my largest power. So I know the numerator will behave like that for really, really large positive or negative values of x. And then I know that the denominator will behave like this. which is its largest power. So if the numerator is acting like its largest power and the denominator is acting like its largest power, this crazy function is acting like this. And I can simplify this because I've got common copies of x. So my hunch is that this function is going to look an awful lot like this function at the end, the left and right endpoints of my graph. So I will show you. This is just something that I can show you. You don't have to plug this in too. So 2x to the 5th plus x to the 4th minus x squared plus 1, and then in the denominator, 3x squared minus 5x plus 7. So that's the first graph. Now, we don't care what's going on in here. We care what's going on at the ends. Big positive and negative values of x. Next, I will plug in what I am claiming to be my end behavior model. So 2/3 x cubed. Okay, so not all that similar from what I can see, but I'm still pretty zoomed in. So zoom out, and you'll see what happens. So I'm going to zoom out. I'm going to zoom out. Oh, I only had to really do it once to see how similar these are? I'm going to do it one more time. And they really get to the point where they're nearly overlapping each other. We don't care what's happening in here. That's why I zoomed out. The end is what's important. The larger values of x you plug in over to the right and over to the left, the more these functions start to mimic each other. All right, so this is your end behavior model for part A. We're going to do the same thing here. Look at the larger two. And notice these have the exact same power. So this, the numerator behaves like 2x cubed. The denominator behaves like 5x cubed, which means overall it's going to act like 2/5. So this is just a number, not a function, just a number, which is a horizontal line, also known as a horizontal asymptote. Okay, so do you guys remember those crazy rules that you probably learned in pre-calc that had to do with the powers? And it was the horizontal asymptote rule test or whatever. And one of the rules told you if the degree of the numerator is the same as the degree of the denominator, then you take the ratio of the leading coefficients. Hopefully that sounds familiar. Well, that's exactly what happened here. You had another rule that said if the degree of the numerator is larger, there is no horizontal asymptote. Last one would say if the degree of the denominator is larger, the horizontal asymptote would be 0. All right, so kind of all ties in together some of the stuff that you guys have learned in pre-calc. So last little bit here, end behavior model. We say G is a right end behavior model if and only if this is true. Okay, so as you go off to the right, if the functions are so similar that it approaches 1, and then on the left, you would just do negative infinity instead of positive. So the last little bit we're going to do on the next page is going to talk about how you can prove that something actually is an end behavior model. All right, so last little thing here. We've got this function right here, x plus e to the negative x. We're going to show that this is an end behavior model on the right, and this is an end behavior model on the left. Okay, so a right end behavior model, you check the limit as x approaches infinity of f over g. So we're going to do this. Okay, and we're going to show that that comes out to be 1. So remember that funny little trick where we split the numerator and denominator? So we can put x over x, which is just 1, and then plus e to the negative x over x. And this is that algebraic manipulation thing we talked about a couple lessons ago. We are just going to keep manipulating that function until it becomes clear what the limit is. So 1, I'm done manipulating that. E to the negative x, remember negative exponents get flipped. So I can write this like so. Okay, so now we're just going to think about this, and this should hopefully make sense to you. If I plug in an incredibly, incredibly large value of x, picture this as being like 1,000,000. That's a really big number. E to the 1,000,000 is far beyond that. So I have an unimaginably huge number in the denominator, and 1 over that huge number is 0. So we got 1 plus 0, which is 1. So the fact that this comes out to be 1 goes along with what I wrote on the previous page. So it's like, yep, check. It's definitely a right end behavior model. Next, we're going to check the left end behavior model and show that as we go off to infinity, negative infinity, I'm sorry, this would be a good model. So f over my end behavior model. And so again, just the algebraic manipulation. We are going to just simplify this as much as we can. So we split them both up. So x over e to the negative x plus, and then e to the negative x over e to the negative x is 1. So that's my function. We're doing kind of like opposite simplifying that we were doing up above, because now this e to the negative x is going to flip up to the numerator. Okay, so now this. Say I plug in negative infinity. E to the negative infinity is going to be so teeny tiny that it doesn't matter what I'm multiplying this by. So this is going to approach 0 just like this one approached 0. And so this approaches 0. This, of course, is 1. And so I proved that since I came up with 1, that is in fact an end behavior model. So let me show you just really quick. I'm going to plug all 3 of those in. So start with my original function. Okay, so that's my function f. So we're saying that as we go off to the right, it's going to look like a different function than off to the left. So as we go off to the right, it's saying it looks just like the function x, which you can see that already. But I will add that in just to show you. And add in an x. So you can see that. As I go off to the right, it looks just like that linear function. But it's saying that as we go off to the left, it's supposedly going to look like this exponential function. And you can see that too. Not as clearly because I'm zoomed in, but the farther you go out, the more these are going to mimic each other. So off to the right, it looks like x. Off to the left, it looks like e to the negative x. And we prove that using a whole lot of algebraic manipulation. Okay, last thing. Oops, I should just keep that up. Use a graph to find this limit right here. Okay, so the sine of 1 over x. Oops, over x. Okay, so as x approaches infinity, it does a lot of wiggling in here, a lot of oscillating, and then it starts to go off like this. And over here, it does a lot of oscillating, and then it goes off to the right like this. So just looking at the graph, you can see that it's definitely approaching 0. Okay, so let me show you the graph. It does, like I said, a lot of wiggling right here. And then it finally ends up above, and then it kind of goes like that and just goes off towards 0. And then this does a lot of wiggling down here, comes down one time, and back along 0. Not the greatest graph in the world, but it pretty much shows what this is going to do. The limit comes out to be 0. And really, this was specifically only asking us for the right-hand side, but off to the left-hand side, it's also approaching 0.